This is Module 12, Lesson 4. We're now going to talk about changes of state or phase changes. We've spent time in the previous lessons learning about solids, liquids, and gases, so now it's time to talk a little bit about what happens as they turn into each other. So first, this is like the other lessons. You need to pause a moment and write these things down, or at least make sure that you remember them. And when you're ready, you can continue and we'll discuss. So I've listed these together in terms of pairs. So in other words, sublimation and deposition are opposites of each other. Vaporization and condensation are opposites of each other. And then melting and freezing are opposites of each other. So you need to make sure that you understand what they are. Remember that sublimation is when a solid becomes a gas, and deposition then would be when a gas goes directly to a solid. Vaporization is liquid to gas, liquid to gas, and then condensation is gas to liquid. Melting is solid to liquid, and then freezing is liquid to solid. Now, I have listed them so that the three endothermic phases are here together on the left-hand side, and the three exothermic phases are on the right-hand side. Exothermic means that they have to give off heat. Like they must get rid of heat in order to do that particular process. Endothermic means they take in heat. Look at the endo and the exo. They take in heat. So these all have to warm up in order to happen. Exo, heat has to exit. So these are all cooling processes. Now, looking a little bit at sublimation in particular, I have some of the information that I just said is right here, that it's going directly from a solid to a gas. It happens whenever the vapor pressure of a substance exceeds the atmospheric pressure. And there's a few examples here that you might be familiar with, like dry ice. The process is used to make freeze-dried coffee. Solid air fresheners, like the ones that are shaped a little bit like a cone, and then at the base they go down like the Renews-It or the Glade ones, and you twist this up and around, and when you do, it exposes the little kind of gel type stuff inside that my kids always wanted to stick their fingers in. That is sublimation. The little piece that's inside of this over time just gradually looks like it disappears because it is turning into a gas. Okay, now phase diagrams. Take a moment to write down all of these vocabulary words over here to the side, and then we'll discuss what they mean. So a phase diagram is this thing right here. This is one example of one. It's a graph that represents the differences between solids, liquids, and gases and their relationships between each other. So you could call a gas a vapor, as this one does. The lines are what's called equilibrium conditions. In other words, if you are on, let me pick a color that's different from what's up there. If you are on this line right here, where I'm putting the red, if you're on this is the line where you have an equal amount of freezing and melting happening at the same time. So this line represents the melting point and the freezing point of water. Okay, the line now that I'm going to color purple, right here, the curve, and that is not good on my part, but close enough, whatever. This line right here is the line between liquid and vapor or gas. So what that means is that this purple line represents condensation and vaporization. So if you follow this line, it would basically be the boiling point of the particular substance. And then if I pick a different color, maybe this teal color right here, this line right here at the bottom that I'm making darker and darker with this color, this represents the boundary between solids and gas, so that's sublimation and deposition. So if you were given a graph like this and asked to find the boiling point of this particular substance at a given pressure, like if it said find the boiling point at 101.3 kilopascals, then you find the pressure on the side, you follow it over. Now what you're going to have to know is where boiling occurs. You're going to have to know that this line represents boiling, because most of these on like the final exam, they don't have any words on it. They just have the axes labeled, and this isn't labeled as a solid, this isn't labeled as liquid, and this doesn't say gas. It's up to you to know where these things fall. It's always in this particular order, and it should make sense that the lower the temperature you have a solid, mid-temp is a liquid, and then the most extreme is the gas part of it. But you're expected to know that this portion of the line where my cursor is represents the boiling point. So if it asks you for the boiling point at 101.3, you just plot your point right here, and then you go down, find your temperature. So the boiling point of water is 100 degrees Celsius at 101.3 kilopascals. If it asks you to find the freezing point at that temperature, then you know that it's this line, the red line. And so you find the point over here that matches up with 101.3 right there, and then goes down. Read it, it's 0 degrees Celsius. Okay, the triple point. The triple point is this point right here. Let's see if I can pick something even different that'll still show up. Maybe this green color, this grassy green color right here. The triple point is where all three states of matter exist at the exact same time. And yes, it really does happen. So you can have water occurring as a solid, a liquid, and a gas, but you must have it at 0.61 kilopascals and 0.016 degrees Celsius. You have to get it at a particular temperature in order for this to happen. In your lesson for this particular module, on the Canvas page that has the instructions and the link to this video, I've also included a link to a YouTube video that shows you nitrogen occurring at the triple point, where you have a solid, a liquid, and a gas all occurring at the same time, so you can just have some idea what this looks like and that, yes, it really does exist. You could do the same thing with water that they're doing in the video, but you would have to get it down cold enough and at a low enough pressure. Okay, the critical point. That is this point right here, and I'll tie that over here to critical point. The critical point is the temperature that beyond which there is no difference between liquid and gas. So the critical point for water is, since you can't read this, is somewhere above 100 degrees Celsius and well above 101.3 kilopascals. If we had a better graph with actual numbers on it, you could actually plot those points and tell me the temperature and pressure that the critical point is for water. So, down here I'm telling you to be able to interpret the graph. So some other things that you could be asked would be things like, if you had water at 100 degrees Celsius and 101.3 kilopascals, you're right here, what would happen if you lowered the temperature, but you kept the pressure the same? So you could picture if you lowered the temperature but kept the pressure the same, you might end up like right here or anywhere along this line. What would happen? Well, it would condense and it would turn into a liquid. You could also ask the same thing here. What if you had water at 0 degrees Celsius right here and 101.3 kilopascals, and you raise the pressure? So if the pressure went up and you're still at 0, what's going to happen? You're following this line right here. Well, then instead of like melting or freezing, because you're right at that borderline point, you would definitely have a liquid. If you decreased the pressure, then it would go ahead and freeze. This helps explain, like, if you've ever had an ice cube in your hand and you've squeezed it really, really hard with your hand, it melts faster. Why? Because you are raising the pressure, and see what happens when the pressure goes up? It helps to turn it into a liquid more quickly because you're into the liquid range more. So you have some practice problems with this. Somehow I managed to draw on this page. You have some practice problems with this where what you're going to do is answer some questions like we just did with the phase diagram. And you're also going to answer just some general concepts about phase changes. So if you need me, I'm available during office hours, or you can send me a message, and good luck with practice.